grid-connected DC converter. So before we start next, I'm going to briefly say what happened. But do we have any questions, concerns, comments? No? Okay. So we discussed about the three different types of the converter system: grid forming, grid volume, and grid connected converter. So you know that grid forming is a form of current source, and grid following as a voltage source, and grid connected can be also used for the regulation of voltage or grid. So then we discussed about the park and collect transformation, and we said that park is used because we can transfer from 3-dimension to 2-dimension, and after that we can actually the variable in fundamental frequency will be DC, so controlling will be much more easier for us. And for the Clark transformation also, we can change it from 3-dimension to 2-dimension, but then it's also sinusoidal with the 90-degree phase shift. So for the design of the control technique, we mentioned that we need to provide the dynamic model of the whole system, because we should see that impacts of each components in the system, in the changes in other parts. So the dynamic analysis started from the converter. So voltage is equal to phase voltage plus voltage of common mode. So by this we calculate the KVL from the system, and then we said that it is not needed. You go through the converter side, you can just simply say that we have a point, 2 point that between we can have some components, and based on that you can provide your dynamic model. So after that we replace with the voltage of the DC side to AC side, and we calculate the switching state function, and after switching state function we replace it to dynamic model of the system, and the matrix also can be reduced from 3-dimension to 2 because of we have no homopolar value and we have the balance system. So then we transfer the ABC to DQ transformation system, and the reason is that we are going to use for the control, because the filtering and the other part in DQ operation is much more easier. So for this we have phase 1, actually phase 2 and phase 3. So we transfer the dynamic model from ABC to DQ, and we reach to these equations. And we also notice that we have the coupling part in this equation, so it provides the negative impacts from D axis to Q axis and from Q axis to D axis. So then we use actually PLL, or we use by calculation of the V alpha and V beta, we could somehow calculate the instantaneous angle of the grid, and if we consider the direction of VD toward the reference value, then VQ will be equal to 0. So based on that, the equation can be also reduced one part, and then we provide the VD as a reference voltage for us. So now we consider also the dynamic model for the design of the controller, and we said that for this we use the PI controller, so we consider the LDI to DT plus RI equal to lambda, and lambda is also the change of the current times to K P and Ki over the S. So we are just talking about what we discussed. Hey, welcome back. How are you? Long time no see. So you're better? Okay, I noticed yesterday in Hyderabad he was in the temple. Actually, this I don't know what they know. No, no German or no. That restaurant was he with the rice and chicken tandoori. Yeah, yesterday. Okay, good. Now you recovered. Very good. So, two what? Surprise for me. Yeah, sure. Why not? You brought tandoori for me? So, okay, thank you very much. Yeah. Okay. So you bought something for me?
Yes.
Okay. Thank you very much. Ah, okay, tea.
Sir, tea nahi hai, sir, cookies.
Coffee and milk. Okay, cookie. Thank you. Okay. Thank you very much. Yeah, thank you. Yeah, thank you very much. Thank you. Thank you. Thank you. Thank you and thank you. Okay. You can, yeah, sure. You can take 10 photos now. Yeah. Thank you. Thank you. Thank you very much. I appreciate. Yeah. Okay. Okay. In the morning. Today. Wow. Okay. Good. So, you're leaving us? Okay. Now the mission completed and return back to okay. Okay, good. Thank you very much, guys. So, now the question is from Arya that do you know why we consider delta I? Okay, no. So, you should listen and then rest of the course will be also easy. I'm pretty sure that you can. Yeah, but listen carefully. I know that you were married, you were actually you had some problem, but now you're recovered. Okay, good. Good to see you again. So, I mean, we consider the lambda as LDI to dt to make our equation more easier, but then after delta I, we have actually this PI controller that tune the output current with the input current. So then we provide the actually model of the system with based on the equation we get from here. But the only things that we consider was that after delta I, which is coming from the output current minus reference currents minus output current, we have delta I, and after that we have PI controller. So PI controller provide the way to follow the injected current precisely the reference current. So we had also this coupling part, and the coupling part provide actually some impacts, negative impacts to the other one. So assuming that we are going to inject just 10 kilowatt power from converter to the grid, and you see that when we have this actually this power injection, we see the impacts of the coupling in the Q axis. But the expectation is that we just inject the active power. So for this, we use some virtual impedance, and based on that, we remove the impacts of the coupling and we decouple it. So we call it decoupling by this way. So by this, we have to separate actually transfer function, and based on this transfer function, we can easily provide the value for the K P and K I. But basically, K P and K I, because of the several other reasons, you cannot say that exactly can be calculated by this equation. So for this reason, we actually can get a quite good idea about the operation of the system, but you cannot provide the exact value. So for example, in copy, we have one omega n, and omega n is in somehow natural frequency, normally is very high. So for this case, if we compare the system, this equation copy with Ki, we see that, for example, if this is 20, then it should be 400. So always you can say that, I consider something as a constant value, but far from each other. So if it is 50, you consider for copy, Ki should be 2,500 something, but then play with the value, reach the right one. And how you can reach then to right value, you can actually check the value of the delta I, and you see that when it is getting better or not or worse, and then by this you can tune the copy and Ki. So then we also consider the power equation for calculation of the active power reference and reactive power reference. And we say that, based on the objective of the integration, you can consider what kind of power you are going to inject. So in one case, if you are going to just inject the active power or combination of the active power in fundamental frequency or harmonic frequency, or later we saw that, how we can actually calculate the reactive power injection. So based on that, you can decide that what is the share of the active power can be compensated, or reactive power can be, basically we are interested to compensate all reactive power, because then we should pay the penalty to distribution grid, but we have also, if we have extra power, we can also consider some part of the power injected for the fundamental frequency of the active power. So this is the model that you will use tomorrow for the simulation. It's not something, I think that at the first day, if you look at this one, it was very complicated, but nowadays I think that this is very easy for you. Am I right? Yes or no? You, at least you can say that there is nothing that I don't understand. For example, reference generation or generator, you must know that what is this, or probably PI controller, what is the idea we are using PI controller, or how we can calculate the switching state function from the equations, or about the alpha, beta, or DQ, and also how we can calculate the theta. But one aspect is this, and one is the tuning of the system. So basically, what I can say that, from my expectation, all of you guys should know that what is the reason that we are using this equation, but then you can apply by the simulation. So, any questions so far? No. So we discussed about the different types of the analysis, simulation result, and yeah. This one? Yeah. Mm-hmm. Mm-hmm. No, you can actually, for the simulation, can consider the DC voltage source here. You don't need to consider this one, because it doesn't matter if you have the AC source or DC source, but the idea is that we are using the DC AC converter. So we should have a DC voltage here, okay? And the idea of this chapter was to control of the DC AC converter. So by this assumption, the left side should be regulated DC voltage, and right side should be AC voltage. Any other question? No. So now I just simply ask one question and then jump to the other. So, Dashida, am I right? Okay, good. Because I have a friend, his daughter is Arshida, Then I think, okay, it was Arshida, then Darshida. Okay, so now I pronounce well. So Darshida told me that, explain that what is happening here. You were also Hyderabad, yeah? Okay, good. Seems that you are fresh and you had lots of fun. Okay, explain clearly that what is happening there. She's looking for an excuse, fall down, broken, and then said that, okay, now, okay, tell me. Clearly said that, I know that, pretty sure that you can answer. So, we start from here. From here. What is this?
We are tracking the reference.
You can use that one.
We are tracking the reference current.
Yes. What currents do we have? Yeah.
Active current.
Yes, in the axis, yeah?
Yeah.
So you see that this is not DC, so it is a combination of, yes. So what is this?
A harmonic.
And fundamental frequency.
Yeah.
Excellent. So it means that the load we have is a nonlinear load, okay?
Yes.
So what is this current? What is this current? DG is connected to the grid, yeah?
Yes.
So compensate all the active and reactive power, okay?
Okay.
So, and this is also, we see that, it's all harmonic and fundamental frequency in reactive side is also compensated, okay?
Okay.
So, and when we reach in 0.2, what happens?
Increase the load.
Exactly. The load increase, okay?
Yes.
But we see that all the reactive power are compensated, but some part of the active power are compensated, but you see it is not following exactly.
Yes.
And what is the reason?
Power is less than expected.
Yeah, exactly. The power actually we have available is less than the
Expected.
load.
Yeah.
Yeah. Okay. Excellent. Thank you very much.
Thank you.
Yeah. So by this assumption, we can conclude that you can control your converter in a way to inject any types of actually compensate any part of the load which is in the priority. So for example, if I have a load that needs reactive power, then my priority is not to compensate the active power. My priority is to compensate the reactive power, and if I find more power available, then I can go through the active power. Because buying the active power from the DSO is much more cheaper in comparison with the reactive power. So now today we are going to talk about the operation and control of converter-based synchronous generator. So it means that we have actually generator or DC-AC converter, but the reaction of converter is not like the previous chapter. It was not just a controller. It provides something else that instead of considering this as a converter control, we are actually going to emulate the behavior of the synchronous generator in operation of this type of system. So at the end of this chapter, you will be able to define the inertia and explain its rules in power system. You will be able to emulate the behavior of the synchronous generator using grid-connected DC-AC. What is this? Oh, okay. Okay, good. And you can provide the required inertia for power grid with grid-connected converters. Support the grid voltage and frequency regulation through grid-connected converters. So, before we start, what is inertia? You remember Costa? No, Abe? Yeah. So, if you remember it, I forget your name, sir. What was? Yes. Ramon? Rahul. So you fully remember actually Abe. And you know that he touched me and I touched him and he was a high inertia and I was low inertia, okay? So now briefly say that what is inertia? What is the definition of the, I mean, don't need we go, just friendly say that inertia is like this, resistance, something like this, again changes or motion, something like this. So, can you provide the better definition of inertia in any system? So it's like our resistance against changes or motion. Yeah, yeah. So, yeah. So, you know, when you are in the bus, okay. So when we start to go forward, we see that we fall somehow left, and when we stop, we fall down. Okay. So this is because of the inertia, which refer to the resistance to any changes. So any changes can be actually when we are in the motion time, it likes to go forward, and when if we are in stop, it doesn't like to go forward or changing. Okay. So the inertia has this problem. I mean, no, has this characteristic. So assuming that if we look at this one, what happens if hamster will suddenly stop? Okay. So when it stops, you see that the inertia also, I mean, force him that just changing or rotating by this way. And if we see this one, the elephant stop, blowing air on pinwheel, we see that when stop it is still rotating. Okay. So this is the inertia that when you stop imposing any energy or power, still it continue. So this is somehow the tendency to stay in the same situation. So in power grid also we have inertia to keep the reliability of the power system or stability of the power system. Basically, the reliability and stability of the power grid is coming from the inertia. So inertia is basically the main source that keep our system reliable. So assuming that this is the synchronous generator, we see that we are in the grid and we have thousands of synchronous generators provide the electricity and support the loads. So we see that this is actually different types of the synchronous generator happening here. And we see one actually in this situation, the power we provide for the loads are the same, so we have a stable operation, so the number of the generation and consumption are in the same situation. But if a fault happening in this system, okay, so then still we see that all components or loads are working, and then some problem happening because the number of generation reduced, so it seems that generation are not enough to supply the loads. So it is like I'm walking and someone actually have a backpack, and then someone put a stone, 3 kilos of stone in my backpack. So it reduced my speed. So nowadays, we see that the generation, now there are some stress because the consumption are more. So for this case, we used actually we measured the frequency, and for example, if the frequency is 60, we see that it dropped to 59 or something like this, and we have somehow a device, we call it governor, that detects the changes in the frequency, and based on that, it calculates and provide the information that, what is the spin of the generator, and based on the situation of the frequency, it provides actually to change this spinning goes actually faster or slowing down. So this is somehow the main mission of the government. Then after sometimes you see that the frequency jump from 59 to 60 again. So this is like a cruise control in power grid. So I mean governor detect the frequency, and based on that provide the information to the generator to increase the speed or reduce it. So when the fault happening, when the generation is less than consumption, it means that we need to increase the speed. So assuming that these things happening, so it means that the fault happened, generation, actually detection has been done by governor because the frequency drop, and this is because of the number of the loads are constant, but generation reduced, so generation are less than consumption. So then governor provide the information, and detect it and provide the information to generator to increase the speed to somehow compensate these changes. So this is something that we need because we have the mechanical devices. We detect it, and based on that react it. So it takes several seconds, and so what happened? So I have a problem, but I can survive. It means that some things keep my system still reliable and stable, even the problem happening in this network. And this is the duty of inertia. So this kinetic energy somehow provide the situation that all the loads running still in a stable operating condition during this transient time. So for, I don't know, 5 seconds something, when the generation is not enough for the consumption, but still the network can stay stable. So this is the duty of the inertia. Any questions so far? Was clear? Yes? So, Siddhant, can you explain what is the responsibility of inertia in power grid? Look at my eyes and explain. Tell me. So, inertia is an energy. When the problem happened, it means that the grid should be unstable. So it means that the generation is less than consumption. But inertia keep the stability or guarantee the stability of the power grid during this transient time. So this is the meaning of inertia. So if you return back to the first day when I talked with the Abe, and then my body's inertia prevent to falling down, okay? So if I have less inertia or the grid has less inertia, it means the time for keeping this stability is less. And as much as we have more inertia, in fact, the system is working more stable or longer time for the stability when the transient or some fault happening in the network. So is it clear so far, Udaya?
Yes. And what's the effect on the frequency about this inertia?
Yeah, I mean, yeah, yeah. So basically, when we have the less generation, so it means that the frequency be unstable. So in fact, this inertia support this fluctuation in the power grid, in the frequency of the power grid. Yeah. Any questions so far? Is it clear 100% for all? Yeah? Arya? Okay. Yeah. Loader. Slow down what? Yeah. Yes. Mm-hmm. Yes. Generate. What happened? I mean, when the load is less than generation, so yeah. So, is it fine? So we can go next page. So nowadays we have a lots of target to provide the electricity from renewable energy sources, and then the main idea is that reduce the greenhouse gas emission, and for this case we need to use the power electronic converter as a heart of interfacing system between generation and consumption. So this type of technology are very very good when we have actually enough inertia in the power grid, but when the generation goes more than 30% in the power grid based on the renewable energy sources, then some instability issue in the frequency is happening, and this is due to lack of enough inertia for the power grid. So for this case, if you look at here, we have the renewable energy, we have the converter, we have the filter, and we have the grid. But the things that we are actually somehow lacking is that this type of technology cannot provide the rotating mass. They don't have rotating mass, and they cannot provide the inertia for the grid. And then the problem is happening for the stability of the grid. So what are the consequences of the technology? I mean, lack of inertia. Then we see that the frequency drop, and somehow stability of the frequency will be weaker, and when changes happening. So if you look at here, we see that we have a actually system with enough inertia and without enough inertia, and a fault happening in this time. So a fault or disturbance happening, overload or something happening, we see that the voltage drop, frequency drop is less. So you see that frequency from 50 goes to 49.96, but in this you see that it goes to, actually we have a bigger changes for the frequency. Why? Because the inertia is not enough for that one. And we have also some factor, we call it Rokov, or rate of change of the frequency, and it's more dependent to the rate of the, actually it's like a we consider the Rokov based on the value of the frequency drop in the power grid. So if someone said that, okay, Rokov of the system, it means that the RAM in the frequency actually we consider like a Rokov. So up to here we see that we need in India, for example, we are going to reach the provide the electricity from renewable energy by 2070. In Europe is 2050. In Finland we are going to reach carbon neutrality by 2035. So, but the problem is happening because this type of technology are based on the power electronic converters, and this type of converters cannot provide the inertia. And so by this assumption, should we need to be worried about that one or not? Any idea? Yes or no? Darshida, do you have any concern about this technology? using the or providing the electricity just by renewable energy in India? You say no. Yes or no? Why?
So no concern because renewable energy is the need.
Okay, it's need, but it cannot provide the inertia and the system will be unstable. So,
But I think within the upcoming years, like the problems, whatever in the market we are facing, that may be sorted.
no, definitely it will be solved, but then how? You are the engineer, you are a smart guy, and then so you are going to build the future in India. So then do you have any idea about that one? Sami? Sami? Do you have any idea about the problem appearing in the future of network of the India if we have more than 50% renewable energy?
When we are going to increase the more renewable energy into the grid,
Hmm.
whenever the fault occurs,
Hmm.
it is going to fluctuate the other systems.
Okay,
The stability may lose.
but my question is something else. My question is that in India we are going to reach the carbon neutrality by 2070, if I'm not wrong. I heard from someone. Then it means that we must increase the share of renewable energy sources, and these type of sources are connected to the power grid by use of the power electronic converter, which they don't provide any inertia for the grid. So it seems that future grid will be suffering from lack of inertia and lack of stability and reliability. So do you have any question, I mean the solution for that, or is it feasible to go from this direction or not?
Definitely we require solution.
Mm-hmm.
Definitely we require solution to provide inertia. That's why we are going to prefer those energy sources,
Mm-hmm.
energy storage devices.
By using the storage devices provide the required inertia.
Uh,
How?
Whenever the fluctuation happen, if suppose our side like super capacitors is there,
Mm-hmm.
at the dynamic state initially those are more power dense devices.
Mm-hmm.
Whenever the fluctuation happens, immediately those are reacted and the sufficient energy is going to supplied by those super capacitors.
A supercapacitor has a very limited capacity, yeah, for sure.
And we are saying like that the super capacitor is there as well as the energy storage devices is there.
Mm-hmm. But the other energy storage are not that much fast enough. So there is something missing, okay? So we see it. Okay, excellent, thank you. Udaya, do you have any comment? It's fine up to now. Okay, so it seems that there is something missing, and then we must provide electricity from renewable energy. We need to use the power electronic, but if we go further than 30%, then we have the instability in power system. So now we see this one synchronous generator. We see that using the conventional synchronous generator is very, very important because they can guarantee, I mean, they have the rotating mass, they provide actually this kinetic energy, and they are very strong against the changes, so they provide a very stable DC voltage in power system, and then by this assumption we see that they are very, very good, but the problem is that we cannot use this one for the renewable energy sources. So this is some things that we are suffering. But the question is that can we consider or emulate the behavior of the synchronous generator in the power electronic based generator or not? So if we get back to the structure of this generator, we see that we have a DC current that applied to the rotor winding, and then we provide the magnetic field and provide then the other external somehow a provider like a wind turbine apply the power as a mechanical power and rotate the shaft, and based on that we provide the electricity. So by this we have actually somehow providing kinetic energy by this rotating mass, which support the stability of the grid. And basically this type of technology are coming from the swing equation of the synchronous generator. So it means that P mechanici and P electrici. So it means that input power and output power, because we are talking about the generator, and the generator is a type of machine that convert the electric or some other types of the power to electrical power. So by this, our input is mechanical and the output is electrical, is equal to j omega d omega to dt plus d times to delta omega. So this swing equation is based on the frequency fluctuation under active and reactive power transition, which are limited by the inertia in synchronous generator machine. So we have also damping factor, but this has a lots of mechanical and electrical limitations. So by this, they are actually damp the fluctuation, but they are not that much efficient to efficiently damp the fluctuation. So they are quite good and strong, but they are not feasible to be used for the renewable energy sources. But the solution for that one is that we use actually some type of technology based on the power converter, and also apply the behavior of the synchronous generator in the control of the power converter. So for this, it could be converter-based synchronous generator, or we call it VSG, virtual synchronous generator. So it means that we use the converter, but control it based on the synchronous generator model. And what is the benefit? The benefit is that we can integrate renewable energy sources to the power grid. Beside the active and reactive power injection, we can provide also inertia for the grid. So by this assumption, the grid, also the inertia in the grid increase by increasing these renewable energy sources to the grid. So if you get back in the 2000 something, 9 something like this, when they reach in the point that when we increase the share of renewable energy sources more than 30% in the power grid, then the inertia is constant and we reach to frequency problem. By using this technology, we see that we can provide required inertia for our system, and when we increase the share of renewable energy sources, in parallel the kinetic energy also increase, and then grid will be strong enough to be survive. So if you look at this one, it works like this one, not like this one. So if you have a virtual inertia or providing inertia in the control loop of the converter-based generator. So now we have actually inertia constant, which we shown by H. So it represents the stored rotational kinetic energy in a synchronous generator or power system per unit power rating. It indicates or shows how much energy is available to resist frequency changes during a disturbance. So H is the kinetic energy stored in a rotor over the maximum power of the generator. So if we said that we have a 20 kilovolt ampere generator with the 1 kilo, kilogram over meter square J, it means that you should calculate the value based on the kinetic energy and divided by 20 kilovolt ampere, 20,000. So basically, mathematical model is expressed by this because the kinetic energy is 1 over 2 j omega 2. This is from the elementary school or high school, I mean middle school, that kinetic energy is 1 over 2 j omega 2. And S is the apparent power of the generator. So by this, H can be calculated by this equation. We call J, here also we had moment of inertia, and then we have omega G synchronous angular speed, and is rated apparent power of the machine is the S. So, question, do you believe that if H is bigger, our system is stronger, or when H is smaller, our system is stronger? Smaller, bigger. Why? Mm-hmm. Okay, great. So when H is bigger, it means that the kinetic energy in power system or system is more. Okay? Then what is happening? So if we have less H, in fact we have less kinetic energy, and then if any changes happening in the frequency, we cannot damp it so fast. But when we have actually higher H, it means that we have more kinetic energy, and if any changes happening in the system, we can damp it faster. So just a simple example, but again return back. Does anybody can say that easily say that what is the H?
Unit of H is second.
Okay.
So it indicates in abnormal situation, machine transfer energy for that second, that much second.
Why? Why that much second?
Yeah.
Not less or not more?
I don't know why less or more, sir, but
Is correct.
H
but
is
why?
fixed.
So why? Why that second? I mean, not more or less.
I don't know why more, sir.
Okay, but thank you very much. It's almost correct, but the first part. So does anybody has any idea? What is the exact actually meaning of the H? Okay, let's see in the next example. So we have a 100 megavolt ampere machine which frequency is 50 hertz and has a moment of inertia 10,000 kilogram square meter. And now we are going to calculate the inertia constant in second. I give the material to you, okay? So we see that, okay, H is J omega 2 to S. 1 over J omega 2 over 2 S is J omega 2 to S. And we see that we have the 100 meg and we have also 10,000. We have omega 2 and 2. Omega 2 is 314 y 2 pi f 2 times to 3.14 times to 50 is equal to 300 14. So the final conclusion is 4.93 second. But what is the meaning of this? I have inertia, I have a maximum power in a generator. Then we reach that H is equal to that value. What is the meaning of this? So if I have a generator that size or that size, what are the different things? What is happening? So any idea? So H equal to 4.93 means that generator can sustain its kinetic energy for about 4.93 seconds at full load before depleting. For example, if no mechanical power, for example, we have a turbine, we are actually providing like a shaft of the generator is supplied. The generator store energy would be used up in about 4.94 seconds at full load. So if it's a stop, it still can continue for 4.90 seconds. Okay? Did you get the point? Yeah, it's a time that it can continue the operation, because the reason for that that inertia is that if we get back the first page, we said that is a type of energy which wants to keep the situation as it is. So if you remember that elephant, you see that when they blew and stop it, it's still turning on, and this is inertia, and it's happening also for the system. So when we get back to the power system and a fault happening, so if we had such a case like this type of generator, you have 5 seconds for the governor to detect the frequency, provide the right value, and then give to the other generator to go upper. So after this 5 seconds, close to 5 seconds, then some problem happening for the power grid. So it means that like you have actually 2 chain, and you have some vehicle. You can keep this one. Then after I don't know 5 seconds, you should leave it. Otherwise, your body will be divided in 2 parts. Actually, I'm not talking about our coordinator. He has more power. I'm talking about me. So, okay. Welcome back. You okay? You want to make a break, or you want me to have a break if you feel tired? Okay. So you reach back 4 a.m., yeah? 2:30 a.m. Okay. It was very bad time. 2 p.m. Ah, okay. Afternoon you are taking. Last night. Okay. Very complicated. You were also in Hyderabad, yeah? How was the nightlife?
Nightlife good, but like I didn't see much people in the night.
Much people during the night. Okay. But during the day, you went to Charman or
Yeah,
something? Okay.
Too crowded.
Yeah, and the quality of the food was good?
Yes, great.
Okay, good. So you're not complaining means that everything was good. You're not complaining means everything was good. Yeah, good. Happy to hear. So, any questions so far? So seems that it is not that much. We are just getting a little bit step by step getting familiar with this type of things. But then later again get back a little bit to go further with some numerical exam. You see what is happening, and you will be actually feeling it more. Just talking about some equation is not good enough, so we will get back again to this with some numerical exam later. Inertia what?
If the inertia of the generator is high,
Okay.
the minimum power required to run the generator, that is the problem.
I mean, when the inertia is high, it depended to the size of the system, and then, for example, if you have a generator in this size and that size, they are not the same. And but it doesn't mean that we control something and said that this is we have something by this for this synchronous generator. They are following with the equation. So if you have the j omega 2 times the 1 over 2, so then you can calculate it. But the system, when you go from the converter based generator, so in theory you can say that I can provide 100% inertia, because we said that after 10% increment you should have 1.5% also inertia to share of the whole power and inject to the grid. So then you have enough inertia which not threatening the stability of the grid. Okay, but when we reach in the low inertia grid, so why we are not increasing from 1.5% to, for example, 5%? Do you know why? In theory is feasible, and we see that okay, we add this one and the storage we have, and then we increase something. But in practical, it makes it, the system, the generator, unstable.
One more thing, that wind turbine is there.
Yeah.
It is also with the generator base, synchronous generator base.
Yes, but it doesn't provide too much inertia. Yeah.
Because of
Yeah.
wind speed, we are able to rotate the turbine.
Yeah.
If the inertia is high, it requires more wind speed to rotate.
No, then it makes the like some turbulence happening in the system. Yeah. Okay. Any questions so far? No. It can be one question for the final. I mean, this exam. So don't forget this number, 493. Okay. Yeah. So now we are getting back to the power system. In power system, we have a lots of synchronous generator, and this type of technology are normally when we use in power plants, they are connected together in parallel. So by this, the output impedance of the system is less, and the system are more stronger. So when we are talking about the power grid, and sometimes we said that we have a strong grid, when sometimes we say that we have a weak grid. So what is the meaning of weak grid? What factor makes this grid weak? What? Impedance when it's very high. Less in it. Saturation. Oh, SCR is coming again to the impedance. Yeah, but this is correct. And any other things? So, yeah. So, I mean, when we have such synchronous generators, in fact, we have a very strong actually output voltage. We have enough inertia, and then the other important thing is that this type of technology are connected in parallel. So if we get back to such a system, so assuming that we have one generator here, 2, 3, Tn. So if we connect them in parallel, and all of them has a Z, the same Z, what is the value of the equivalent? Z over 2 N is equal to Z equal. Yeah? So assuming that I have these generations to connect the grid, I mean the load or anything grid. So we see that we have a grid. The Z is equal to N, and this is the maximum power we can get from the power system. Okay? So Z over N. So assuming Z is 1000, and then we have 10 generators, so Z is equal to 100. Okay? So, and then Udaya is a representative of the Minister of Education, Energy and in India, and then they said that we are going to phasing out this generator, and one by one we exclude it because we provide some extra power from wind, solar. So as much as we build a new power plant or some sector for the renewable energy, we exclude one like this. So if we exclude one, it's 1000 over to 9. Then again 1000 over 8. 1000 over 7. Okay? So you see that as much as we exclude the synchronous generator and include the renewable energies, so it means that impedance is going up and upper. Yeah? The impedance increase. So when the impedance increase, in fact, the load changes provide the bigger impacts in the point of common coupling, and then the voltage or system will be more unstable. So get back to just a simple numerical example of this. So we have a grid is, I don't know, 400 volt, and then we have Z equal to 10, and this is a load which the current is 5. Okay? So voltage drop here is 50. So the difference between this voltage and this voltage is 50 volt. Okay? And if we have Z equal to load, Z equal to 8, and then the same network, 400, 360, and delta V will be equal to 40. Okay? And then we go to the same grid, 400, and then we have a load, current is 5, Z is 2. So you see that this is 400 and this is 396, and delta V is equal to, sorry, current is 5, Z is 2, so it is 90, and this is 10. Okay? Sorry, 2. So what is the meaning? As much as our grid impedance is higher, the difference between the voltage over the load or point of common coupling and difference with the grid voltage is more. We have more somehow drop. And any fluctuation here in the load current provide more impacts in the voltage over the point of common coupling. So the system will be always fluctuating because of the load changes. But when we have actually a smaller impedance. In fact, the impedance over the grid is somehow almost similar to the voltage of the point of common coupling, and anything happening, we have a stable voltage there. So by this, when we increase the share of renewable energy sources in power grid and also reduce the number of the synchronous generator, the impedance of the grid increase. By this, the grid become more, become weaker. Okay, so by this, anything happening, in fact, the grid is not as strong enough to damp changes, and we can say that we have very unreliable grids. Is it clear up to here? Yeah. So rest of your life, if someone asks you what is the difference between the weak grid and a strong grid, you can easily say that in weak grid, the impedance of the grid is high, so any changes in the load can have the big impacts over the voltage of the point of the common coupling. But in a strong grid, impedance is smaller or small, then by this, the fluctuation in the current doesn't provide too much fluctuation in the voltage of the point of common coupling. So now we get back to the synchronous generator model, and we see that we have actually this this generator. So this generator, and this is our grid. So grid have the voltage. So based on that, the objective is to have a stable voltage here also. And then we have also synchronous generator that provide the electromotive force in the output of this generator. So we have also the impedance of the generator R plus L. So what we can see is that we have a voltage source here, which is going to connect the voltage of the grid, and by this we have a voltage with E, and the phase can be theta. Theta can be anything between 0 to 360, and the grid also have the theta of the grid, which also can be between 0 to 360. But because we don't have actually something like PLL, we cannot consider that what is the value of the theta in the grid. And always we have actually phase shift between the voltage of the synchronous generator machine and also the grid. So the difference between the grid impedance and the angle of the grid voltage and also the angle of the generator electromotive force is equal to delta, or we call it delta is equal to the theta of the rotating machine and grid. So if we consider this one, we can see that how much power can be injected from the generator to the load center. So if we have E, voltage of the synchronous machine, and also V, voltage of the grid, so the active power can be controlled by the controlling of the delta, because the equation for transferring or injecting power from the generator to the grid is equal to E times to V over to Z times to sine delta. So by changing the value of the delta, we can easily control the value of the active power which inject from the generation to the consumption. But regarding reactive power also, we have the E, and then we have also this equation EV over Z cosine delta minus V2 over the Z, and the reactive power can be controlled by controlling the E, the voltage of the synchronous generator. So by this assumption, we can consider the E V over the Z equal to P max, and in some case that the difference between the angle of the grid and angle of the a synchronous generator is small, we can consider the sinus delta is equal to delta because it's very small value. And by this assumption, P max sine data can be shown by sine delta, P max times to delta, not to sine delta, because they are almost the same. So, is it clear up to here? You see that this is a source, this is another source here, and then because we have a generator, so it means that we are injecting power from the generation to the consumption, so the grid can be considered as a load, and we supply the load. And we can easily see the current injected from the E to V is equal to E minus V, but we consider the phasor, so E with the angle of the theta minus V angle of the theta times over to Z is I, and then the voltage also can be based on the voltage of the grid. So easily we can calculate the power can be transferred from the generation to the consumption, or from the synchronous generator to the grid. Is it clear? This is the simple electric circuit to from the bachelor level in electrical engineering. So easily can calculate the active and reactive power from the machine to grid. Is it clear? So for the next stage, now we have actually this system V is equal to E minus Ri minus L di to dt. Is a dynamic model of the system. Is it clear? You want me to calculate it? Minus E plus L di to dt plus Ri plus V is equal to equal to 0. So V can be calculated by this. So we can, using the Laplace, Vs equal to Es minus Is times R plus Ls. Up to here is clear? Okay. Then, if we are going to model this system in a state of this, because we are going to model in the control loop, then we see that we have the current injected from the machine to the grid. So the current is coming times to R plus Ls, current times R plus Ls, and we have actually E from the synchronous generator, and E minus R plus Ls times to I is equal to V. Okay? So by this, we see that we can model the operation of the system by mathematical equation. But the problem is that when we pass actually the current from R plus Ls, then this current, they have a little bit actually disturbances. Then we get the derivative of the disturbance, so it increases the value of the pollution in the current. So the measured current is affected by a derivative terms for calculating the voltage reference of the power converter. Okay? So did you get the point? So when current pass through this type of actually derivative, it increases the disturbances in the current. Because we are using the high frequency system, by default they have actually the frequency disturbances, then it increases the value. So then this is not a good idea to consider this one. Of course you can use it in the control of the converter, but what we are saying that we have the model of the generator based on the synchronous generator, and the idea is that we are going to transfer this behavior in the loop of the converter. And if we consider this one later as a converter, it means that the injected current from here, which is based on the switching, they have a high frequency disturbances, and when it passes through the LS, in fact, it gets the derivative of the current, and it increases the disturbances from the converter to the grid. So for this case, Pedro Rodriguez is a friend of the Udaya. Yeah, he developed a technology, we call it SPC, synchronous power controller, and said that as a solution for this case, we get back to the same equation, but instead of considering the voltage model, we considering the current model. So again, the same equations, but it goes to E minus V divided by R plus LS is equal to I. I is E minus V over to R plus LS. Okay? So what is happening here? Again, we have a converter which injects a current, and we consider the voltage, measure the voltage, and we have actually this E and E minus V, E divided by R plus LS. E minus V divided R plus LS is equal to I. So now what is happening? Does anybody has any idea that why we are using this one? Instead of impedance, we are using the admittance. But what is the benefit, or what is the difference? Is there any benefit or not? Abe? You are the king of the inertia. Now, do you know what is the reason that we do these things? What? Mm-hmm. Short circuit. Mm-hmm. Why short circuit? Let's see. Mm-hmm. Yeah. Thank you. So you see that this R plus LS working as a low pass filter. So instead of increasing the disturbances in the current of the converter to the grid, it reduces it works like a low pass filter and provide less distortion from the converter to the grid. So this is the benefit of this type of technology that we are going to use. So, any questions so far? So it seems that what proposed by Pedro Rodriguez was not actually complicated, but is very useful in comparison with the voltage model, which provide actually more disturbance from the converter to the grid. But still, we don't see what is the role of the converter here. Does anybody knows that what is the role of the converter here? No. Where do we see the converter here? Yes, but do we have converter here? Where is the converter? Yes, but we have also providing the reference, and reference is going to the control loop of the converter. So when we get back here, in previous session, we discussed about here. We said that, okay, it can be 10 ampere, and then we control the converter and measure the injected current from the converter to the grid, and by this I reference 10 ampere, then measure the current injected from converter to the grid, delta I, we have it, and then we have a current controller, PI controller, and by this we can tune the operation of the system. Copy and call can be tuned, and it works well. So what we do here is that we provide the virtual admittance. So the injected current we consider as a reference from the converter to the grid is somehow less polluted to the high frequency pollution, and by this we can actually ask about the current controller to provide them the power with higher quality. So what we discussed last chapter was this part. Okay? So it means that we provide the electricity and inject the power. So we can say that I reference is 10. We said 10 amperes, so we calculate the 10. If we get back to the previous chapter, so we see delta I. This is the injected current from the converter, and this is the reference. It can be load current, it can be harmonic, it can be anything you want, and the converter injecting based on that one. Okay? But what we are going to actually do here is that provide the reference for the control of the converter based on the behavior of the synchronous generator. And then beside the provision of the active and reactive power, we can provide some supportive functionality to guarantee the stability of the power grid under dynamic operating condition. So up to here, we see that there is nothing complicated. Is it complicated so far? Now we are going to step by step to see that what is how we can actually modelize that one. We here. Hello? Yeah. We had too much, and we said that always we are going to provide the virtual inertia for the power grid and this type of thing, but I don't know, or probably we don't know how we can reach to this value. We can say that, for example, Somi said that we can use the storage devices. Do I pronounce it? The battery is not working well. Hello? Okay. S-U-O-I. So, S-U-O-I. No, I'm saying that check from English to, or from Finnish to, if I'm not wrong. Suomi. Okay. Arya? Have you ever heard about this technology of the virtual synchronous generator, inertia emulation? No. Yeah. Okay. What about you? No. So more than one week I'm talking about this, and you never heard about this subject, yeah? Okay, good. Okay. I cannot pronounce your name perfectly. So, introduce yourself again. Bruna Luni. Murula Lini. Murula Lini. Sorry. Murula Lini. You don't have nickname? Lini. Lini is much more easier also. Lini. We are going to provide the behavior of synchronous generator in the control loop of the converter. Why?
So I don't know.
So relax. I don't know. Okay. Uh, so we talk about the PI controller, the control of the converter. Okay. Now we are talking about the using the model of the synchronous generator, and then our converter react like a synchronous generator in a state of converter, just a converter which injects power. So, do we have any idea, Lenny?
It provides the inertia.
Inertia, yeah. So, okay, excellent. Thank you, Lenny. You're smart. Okay, good. So, this is the only reason? Only reason. More maybe yes, maybe no. Okay, good. So then if I get back to Arya and ask this question that, we are trying to go a little bit slowly, still we are in the beginning, but, it's like what is the intention for this? So why we are going to provide the behavior of the synchronous generator in the control loop of the converter and say that the converter is working like a virtual synchronous generator. So what is the reason?
We are giving it to the control loop, and the control loop from the control loop we are giving it to the converter.
Okay.
So like you are asking the reason. Yes. So like to get the feedback from from the control loop to converter, right?
Yes.
So, like we have to convert a particular parameter.
It is a so. What was your name? Anushri. Anushri. You explain clearly, then listen to her. Did you get the question? Why do we need, thank you. Why do we need to do this? Okay, let me say it differently. In previous chapter, we learned how to use the PI controller, and we saw that, by PI controller, you can actually measure the reference current and compare with the injected current, and after that PI controller, so we can tune the controller, and based on that we can inject active and reactive power and compensate the harmonic current components. Okay? So it means that whatever we want, now we can apply to the controller and obtain. So if I would like to get the reactive power from the renewable energies and compensate the reactive power, I can. If I'm going to compensate the harmonic, I can. If I'm going to consider the combination of all things, I can. So everything is fine. Now the question is that what is the intention this chapter 5 we are going to do? Why do we need also go further? That one is not good enough? What's her name again? Anushri. Okay, Anushri, tell me. Your name is very, very hard for me. Okay.
No idea.
You don't know. Let me help you a little bit more. So we said that in 2009, the share of renewable energy goes more than 30%, and then lots of governments noticed that we have some problem for the grid frequency because it cannot provide enough inertia for our system. Is it correct? So do you believe the previous controller can provide the inertia for the grid? No. We can provide the electricity, but we cannot compensate. So what is the reason for this chapter? to learn how to provide inertia for the grid. Okay? Don't be afraid. Okay, so it's a pretty normal. I can say that, you know, lots of people, or probably sometimes you don't know what I'm exactly asking, but we learn together. Okay? So the idea is not that to make you a little bit guilty. The idea is that we understand we are in the same page or not. Okay? So don't be sad. She was asleep when I explained. You at least were in the class. Yeah, okay. Lenny, am I right? You were asleep? Okay, yes, yeah. That's enough. Okay. So then get back to you guys and you ladies. Do we really need to have this discussion in this chapter? And if yes, what is the reason that we need to provide the electromechanical model of the synchronous generator in the control loop of the converter? No, you are not interested. Okay, they are not interested to answer. Udayat, you want to say something? Mm. Yeah. So then the main idea is to consider actually, sorry. Yeah. Okay. So the main idea is that we provide supportive functionality beside the active and reactive power. So if we get back again, I say one time again that, you know, for integration of renewable energy sources to the power grid, we need the power converter. This power converter cannot provide the kinetic energy for the power system. So then after increasing more than 30% energy from renewable energy sources, then we get in the problem of the instability due to lack of the inertia. So for this case, just providing this control loop and said that, okay, current is this one and inject power, that's off, is not enough, okay? So for this, in this chapter, we are going to provide some supportive functionality by controlling the converter and provide the, for example, inertia, voltage and frequency regulation for the grid, and increase the stability of the grid by integration of renewable energy sources to the grid, okay? So this is the main idea, that beside that current control, we add new functionality to operation of the converter-based generator. So we said that if we are going to consider this, we need to emulate the behavior of the synchronous generator, conventional synchronous generator, in the control loop of the converter-based generator. So for this, what we need is to see that what is happening in the conventional synchronous generator. So in conventional synchronous generator, we have actually the voltage and also the impedance of the synchronous generator. So based on the dynamic model, we see that, you know, we can modelize actually this part in the control loop of the converter. But when these things happening, we have the converter, and this converter is based on the switching, and the switching also provide lots of frequency, high frequency disturbances. So when we pass through this derivative part, in fact, we get the derivative of these disturbances and increase the value of the disturbances in the power grid. So in fact, we inject disturbances to the power grid. So by this case, we change the equation. We said that instead of following the voltage, we just transfer this one to here. E minus V is equal to R plus Ls to I. So by this, we have the I equal to E minus V over to R plus Ls. So what is happening here? It means that, the current we are providing this operate as a low-pass filter. Instead of increasing the disturbance, it filters the disturbance, and we have a better shape of the current for the grid. So it works like a low-pass filter instead of providing more actually a problem for the grid. One time forever, we are going to provide supportive functionality for stability of the power grid by emulating behavior of the synchronous generator in the control loop of the converter base generators. Okay, without that, we get in the problem. Is it clear for all? If I ask this question, it seems that everybody knows, yeah? Where is the Rakesh? Rakesh is not here? Yeah. I mean, it is not the constant number because it depends the grid, but they said that when we reach to 30%, it's something like this, okay? I mean, they said that based on the inertia we have in you said that the structure of the network should be considered. But basically, this conventional power grid are very strong. So if you say that 30% in American network, it is not like a 75% in Indian, or in Finland is not, I don't know, 55%. They are something almost similar. Yeah. Mm-hmm. Yes, but at the end, what we are looking for is not just this one. We want to see that our converter is operating like a synchronous generator. But they have some benefit comparison with the synchronous generator, because in synchronous generator we have a limitation due to just mechanical and electrical components they have. So this damping factor are not working very well there. So what we are going to see is that we have the benefit of the synchronous generator, and also we skip the drawback of the synchronous generator. So this type of technology can provide such a profit for power system. So if I go here, then I cannot stop here. I think that it's better that we close today, because I feel that some of students are a little bit tired. Yeah, you got the point? Everything is clear for you? You. Yeah, okay. Yeah, I noticed that. It's for the exam dates. Wednesday or Thursday? Pattern? It can be like a multiple choice, something like this. And why? Okay. So what is the best day for you? More convenient? Thursday. Mm-hmm. Okay. Okay. So Tuesday we have just a simple exam. So be relaxed. Don't worry. So like a 10 multiple choice, question, and then so shouldn't be too and I don't know if we can go further or not. Yeah. Sorry? Tuesday, yeah. But it's not something complicated. Don't make your life hard for that one, okay? So it's a normal discussion, and yeah, it's a yeah.
Multiple choice.
Yeah, multiple choice.
And
Yes.
one more thing, that tomorrow's laboratory session is going to happen in the Smart Electric Grid Laboratory, which is there, located in the second floor of Electrical Engineering Department. Okay, we'll guide you to come over there
Yeah.
directly.
Yeah.
Yes, morning, 9:30. After having the breakfast here, you take the breakfast.
Now it's okay? Okay. Yeah. So I promise.
Those are the main important grid forming techniques and
Yeah, we go for that, okay?
to control. We will
Yeah.
regularly waiting for that.
Okay. But you cannot learn model predictive all together in one course, okay? Because it's a topic of, I know this probably, you know, Jose Rodriguez from Chile, or Petros Carmanacos, or Vasquez, Sergio Vasquez. They are actually working whole life, academic life in predictive control. Or this Tobias Guerrier is a fellow of IEEE in MPC. Yeah. But we try to actually provide some information, then later up to you that how much you are going to go deeper. Yeah. So, Lenny, is clear for you? First part, no. Second part, okay, yeah? Okay, you were asleep actually, not this first part. Okay, good. Excellent, so we see each other tomorrow. Yeah? Have fun.
Yeah, thank you. You can break for the tea. Tea is